Hi, everyone. Welcome to BIO347, Biostatistics. I'm Dr. Jeff Stratford at Wilkes University. Today's lecture is going to be about data distributions. When you talk about data distributions, what we're talking about are the distribution of outcomes. And we can talk about that theoretically. For example, if you have a fair penny, how do the outcomes turn out? And an infinite number of penny flips. If you roll dice, what are the distribution of outcomes if you have an infinite number of dice rolls? You can also look at things like what's the distribution of human heights. You can look at distributions of all kinds of things, right? When we talk about distributions, they can be described by probability distribution functions. So a PDF, but not the PDF that are used to save documents. So most probability distribution functions kind of have, they come with some equation. We're not going to go over the equations. That's more for a math stats course. We're going to go over what the graphs look like, because we can take those equations and apply it to outcomes. And then I'll show you methods to, later on, I'll show you methods how you compare a theoretical outcome to a given outcome. Okay, when we talk about PDFs of any data distribution, so you think about coin flips, you think about distribution of human heights, the number of white blood cells and a blood cell counter, the number of, or the distribution of patients coming in with a particular disease into a hospital. All those distributions, they take on a particular shape. And we use histograms to explore those shapes. So a histogram, right, is just, we look at the range of X, okay, and then the frequency of those outcomes, okay. So for example, a famous distribution is like a normal distribution. So this would be low values of X, high values of X, and then the average number of X, okay? And that just means there's more average occurrences than there are these other more extreme occurrences. The PDFs, okay, since they are occurring on a number line, you often need a few parameters to show what that shape is. So I gave you one shape. If you can imagine, there's all kinds of other shapes, and we'll go over those shapes. But you need something called a scale parameter, which means, is our data occurring here? Ooh, shark. Here or here, right? So the scale lets us put that data somewhere on this line here. The shape, if you can imagine, means, are we drawing something like this, or like this, right? So here's three different shapes in three different locations. All right. So what I'm going to do is I'm going to go over a number of data distributions and what parameters you need to define those distributions. All right. First one is uniform. Okay. And let me also say that the distribution of outcomes are equivalent to probabilities. okay? They're equivalent to probabilities. So the distribution of a uniformly distributed data, it is what we say X is distributed uniformly. We'll just abbreviate that UNIF with just two parameters. Okay. The shape of a uniform distribution is always the same. Okay, it's what we call flat distribution. The simplest one would be the distribution of outcomes if you look at getting heads versus tails, okay, 50-50. And so what you need is N would be the beginning and 2 would be the end. Okay. Let's give another one, rolling the dice. Okay. There are six outcomes, all with equal probability. 1, 2, 3, 4, 5, 6. What you need to know is the beginning, 1, and the ending, 6. Okay. So in this case, the uniform distribution can be integers, or actually it can be continuous numbers. Okay, and I use the uniform distribution. I'll give you an example of how I used it. You have a hedgerow, and I wanted to randomly put up these model caterpillars and then look at the rates they would be bitten. So let's change the color to green because the caterpillars were green, right? And what I did is I put down a measuring tape, 50 meters, okay, from 0 to 50. And what I did is I put up 20 random caterpillars, and the R code, all you have to do is, I'll actually put it in here, R UNIF, then 0, actually be 20, because I want 20, 0, between 0 and 50. And there was a little bit more to it because since it'll give you continuous numbers, there's way too many digits, and we would just locate it to the nearest centimeter. And what it does is it means the probability of me putting a caterpillar is equal all along here. So you end up putting them here, and here, here, maybe 2 close together in a space, and maybe 1 up here, and so on and so forth, for a total of 20, right? Then you go back a week later and see how many of the 20 have been bitten, and it gives you a predation rate per day. But anyway, so I used the uniform distribution to make sure that the probability of putting a sample anywhere on this line was equal, all the same. Okay. So that's the uniform. Again, it could be counts, rolling dice, or it can be continuous numbers. It's an important part there. All right, next distribution would be the binomial. And the way you write this out would be X, so the values of X are distributed binomially, and we just write binomially with N and P. Okay, where N is the number of successes and P is equal to the probability of success. So for example, we use this when we're looking at the distribution of how many birds you would find at a particular spot. You would use this for out of a pool of 10 people, how many are sick? So being sick would be success, right? So, and then you repeat that and you have your binomial distribution, okay? So binomial distribution, the underlying data are binary. So alive, dead, sick, healthy, present, absent. So the underlying distribution has got to be binary, and it's a distribution that is when you repeat this, okay? So you would use a binomial distribution with things like logistic regression. Okay, with logistic regression, what you're doing is you are predicting whether something happens or not based on some covariates, okay? And you assume a binomial distribution, okay? And that shape will depend on these two parameters, okay? All right, so that one's straightforward. The next one is Poisson, not Poisson. All right. Poisson distribution, there we go. We say that X is not chi, just X is distributed, the Poisson distribution, and you only need a single parameter, lambda, where lambda is the average count. So Poisson distribution is a count distribution, so the data are integers. And so lambda could be 0 and anything above that, okay? 0 to anything above, but here's an important thing. You only need the average because the shape is determined by the average. If we look at a histogram of outcomes, okay, when lambda is close to close to 0, then, well, here's the thing is you have from 0 to infinity, you can't go below 0. So remember, we're dealing with counts. So you can't have -6 sick patients coming into your hospital. So it has to be some number greater than 0 and above. If you are close to 0, what you'll find is things pile up at 0 and then they tail off, okay? So when lambda is close to 0, not even touching the pad, what's up with that? There we go. All right, so when we have lambda, okay, we're going to just say greater than 0. And we can pick some number like 1. So on average, we're getting one sick patient per day. Okay. And we want to know what's our distribution of outcomes. What you're going to get, again, is less. It's going to go a little bump. We're going to get 1 and then tail off again. Okay. So let's do this again. And let's say X is equal to, and we'll say something like 5. Then what you get is same thing. Can't go below 0. It's even lower, goes up to 5, tails off. Okay. And now what happens is as your mean moves across, okay, and let's just say lambda is going to be much greater than 0. Okay, so 20. What you'll get is a distribution that looks like this. So here's 20, and you'll get something like 10 over here and 30 over here. The important thing about the Poisson distribution is that lambda equals the variance. Okay. The variance is the spread in your data. This is the location parameter. So in Poisson, you have a special case where your location parameter and your shape parameter take on the same values. So you always have a very predictable shape. So that's why I don't have to tell you the shape for the Poisson. I just tell you the average, and you automatically know the variance. So the Poisson has a very predictable shape. And basically what you do is when you have a mean close to 0, your data will pile up. And as you get away from 0, it'll actually take on a normal distribution. But it's not a normal distribution because a normal distribution is based on continuous numbers. Poisson distribution is based on count. We'll take on that same typical bell-shaped curve. All right. So that's the Poisson. Okay. The variance and the mean are the same. All right. Who's next? Negative binomial. Okay. The negative binomial is like the binomial. Not sure why it's called negative. I should look into that. But the negative binomial, again, the underlying process is binary, but now we're looking at those things grouped. So would it be how many birds would you sample at a pond if you sampled 50 ponds? Okay. So, or how many sick people would be at your hospital if you sampled a number of hospitals per day? The negative binomial we say that X is distributed negative binomially, and we need R, which is the number of successes and the probability. Number of successes per trial, I should say. The negative binomial is a generalized distribution where for counts, where the Poisson is a special case. It's a special case because the mean and the variance are the same. The negative binomial distribution, you don't have that. So let's say you have a count of 5, right, the average. Then your Poisson may look like this. And then let's use green for a negative binomial. The negative binomial is more flexible in that you can actually have less variation. Okay, so there's one type of outcome. or it could have more variation. So it may look like this with a longer tail, okay? So use negative binomial when your variance and your mean are not the same. The variance and the mean are not the same, okay? So a classic case is the number of parasites. So I know somebody that looked at leeches, of all things, on turtles, and what he found was, let's go back to blue. What he found was that most had 0, okay? And then you found this really crazy thing where some turtles had 20, 30 leeches on them. So if you know a turtle has a shell, and then you have skin on the front legs and back legs, they were all clustered around the back legs. And I've seen turtles like this myself, and there's so many leeches hanging off the back end that the back end ruffles, right? Like it's carrying a bunch of streamers. It's a little bit disturbing. I don't know how badly this hurts the turtles, but the negative binomial is used when you just have more variation or less variation than you would expect with a Poisson. Okay, that's when you use negative. Again, deals with counts. It's not for continuous data. All right, zips and zins. These are fun. So although you don't come across zips and zins in a lot of general text, I'm going to include them because they're super important to things like epidemiology and ecology, which I think captures most of us here. And zip stands for, the Z stands for 0 inflated. Okay. 0 inflated means you have way more zeros than you would expect based on that typical distribution for whatever mean you have. Okay, so you can be 0 inflated Poisson or negative binomial. Okay, what does it look like? Okay. When you do a histogram, and this could be something like most diseases actually will have a 0 inflated Poisson or negative binomial. Let's say you're looking at 10,000 people and you want to know you have some rare childhood disease, and for most populations you'll find that most have 0. Okay. You'll just have this huge number of zeros, and then what you'll find is sampling 10,000 people, you'll find that you'll have a number of cases with 1, right? 1 out of 10,000, then 2, then 3, then 4, okay, then 5. So if this was a normal Poisson distribution, you may find that you would expect this many zeros, but instead you're getting this. Okay, or even a negative binomial. Based on one of these distributions, you get so many zeros, maybe more, maybe slightly less, but what you observe is this huge stack of zeros. And so usually we think about this as a two-step process that generates these data. So initially this came out of manufacturing, and what you had was these would be the number of defects on a shift. And if you can imagine, I think it was shoes, where the machines are working properly and you have lots and lots of zeros. So for a whole shift, you get no defects. Something happens to the machine and then it spits out a number of defects. You can have machines that actually have some error, but are not producing any defects, at least none detected. and then something bad could happen to your machine and it'll spit out a bunch of things. But most nights, if you imagine, or days, over the shift, you're not producing any defects. So this is what the data would look like in that case, okay? So you have two processes. One, when the machines are working properly, okay? They're just spitting out zeros, okay? And then when the machines are defective, they'll mostly put out good shoes, but then they'll spit out a bunch of bad shoes. So you can think about this as, it could, let's say some childhood cancer, for example. You get mostly zeros, and then you can test for clusters because you would have a predicted number based on sort of a Poisson process, a random distribution of outcomes. And if you get more than that, you may be able to detect a cluster. But what's happening is in a cluster due to some sort of, like, let's say contaminated water, some sort of contaminant in the soil, where most people don't live in contaminated areas. So you get populations with 0, 0, 0, 0, 0. Most cases get 0. And then you have contaminated soil, right? And that'll produce a number of cases, but not every kid that's exposed will get a childhood cancer, okay? So you still get zeros for your regular process, but you even get more zeros because you basically have two processes happening. So that's zero inflated. And this could be, for example, if you talk about cancers in adults, what you could have are certain genotypes that never get a particular cancer, and then some genotypes are more prone to cancer, but it doesn't necessarily mean because you have that genotype you get it. It's just makes you more prone. So what you have is a population without the genotype, which would be this one, and a population with the genotype, which would be this one, okay? So that's zero inflated Poisson and negative binomial. All right, who's next? Gaussian or normal? So Gaussian is the name that's also given to a normal distribution. I prefer Gaussian because normal implies something it shouldn't. I think it has baggage on it that if you say you're not part of the normal distribution implies you're not normal or something, but not every biological phenomenon is distributed normally. So that, let's just call it Gaussian. Okay. And what we say X is distributed normally. We should say Gaussianly. What we say normally with a mean mu and standard deviation sigma. So if you know these two things, you can draw a Gaussian curve. Okay. Like I said, there are equations that go with this. I don't want you to know it. I'm not going to give it to you. If you're super curious, you can look up the PDF of the Gaussian distribution. And of course, it'll include these things, but I'll just say you just need two parameters to describe it: where the mean is and then the shape of the curve. This is true for any curve, but particularly Gaussian curves. There's three types: mesokurtic, lepto. So think of kurtic as meaning curve, which it does, or bow, and then platykurtic. So meso or meso means middle, lepto means sharp or narrow, and platy means flat, like a plateau. So these, we'll do meso. Meso is your typical Gaussian curve. Lepto, and I'll draw these with the same mean, but different, and these are driven by standard. So if you had just a tiny standard deviation, it would look like this. And then platy with a very large distribution might look like this. Here's the important thing about these curves, although I didn't draw it exactly like this. If you draw a line down the middle, okay, half the data are over here and half the data are over here, right? So Gaussian curves are normal, and you can actually deviate from this if you add some skewness, but those data would not be Gaussian anymore. Okay, so those are your three types of normal curves. I'll ask you, give you a test and say, are they, I may ask you to draw it, or I'll give a drawing and ask you to define which one those are. All right. I've got two left. So there's a large number of distributions out there, much larger than what I'm presenting here. I'm giving you the ones I think you might encounter in a graduate program when reading the epidemiological literature. So you're going to be a doctor, optometrist, and you have certain occurrence of diseases in the literature you should know about. What I'm hoping you do is these are the distributions you come across, and you can say, ah, I know what that means. All right, two left. So one is drawing here. Gamma, I'm going to leave that line. Gamma. Ugh. Okay, what do I want you to know for the gamma? It's a continuous distribution. So the numbers that generate the distribution are continuous. They don't go below 0, and they tend to pile up on 0. So gamma distributions can look like this, okay? Like a negative exponential decay. Okay, that's the gamma distribution. All right, and you'll see this if you look at the average number of people with a particular disease. You'll see this with epidemiology in particular, right? When the average number is a continuous number, although what's generating as a count, you can still get continuous numbers when you say the average number of people with a disease for a certain population, okay? And so this goes from 0 onward, right? Continuous numbers. The beta is, to me, really interesting. Use beta for proportions. However, your data is confined to be greater than 0 and then less than 1. They can't equal these things. So we've used betas when you know it's going to be some proportion that's not 0 and 1. And you need 2 parameters. So gamma actually only has a single parameter. Beta has 2 parameters because it takes on, there's one that is a shape, and then there's another shape parameter. And you can form all kinds of wacky shapes. Betas can be like this or like this. It can be skewed. They can be normal. Beta takes on all types of shapes, but it's whatever the shape is between 0 and 1. So you use it for proportions, okay? And when data is standardized, well, you still can't go above 1, but greater than 0, less than 1. All right, and there's your distributions. Like I said, there's a few more, but we're going to stop there. And if you have any questions, please send me an email. Thanks.